Good morning to all of you. I think climate change played a trick with me yesterday, so my flight was cancelled. Nevertheless, I look forward to some other occasion to be in CDS. Now, I will try to put across whatever I want to say in 45 minutes. I've kept my watch in front of me. It's difficult because climate change is a vast subject. Is this okay? Is okay? Just a second. The slide is there. Okay. Okay. As all of you know, international negotiations are going on in Dubai at this time when we are speaking. What is called the Conference of Parties, the 28th Conference of Parties is happening in Dubai at this time. It will go on till 12th December. And not much good news is coming from there. But nevertheless, the event is important as part of the global negotiations. As you all know, the IPCC, the Intergovernmental Panel on Climate Change, was constituted in 1988. That was a landmark. And then in 1992, in the Rio conference, the UNFCCC was, the framework was created, the agreement was created to look at evolving solutions for the climate change. In 98, there was another major event. Professor Dr. James Hansen, who was then director of the NASA Goddard Institute for Atmospheric Sciences, he testified before this US Senate committee with proof that climate change is happening. So these are major landmarks. More than 3 decades, we have been discussing climate change. So first, I would like to look at what's happening, what's the good things that are happening. The good news. There are 2 major actions happening around the world in many countries. One is, of course, transition to cleaner forms of energy, in which my institute began working in 2004. When nobody was talking about renewables, we pioneered the studies and discussions and conferences in India on renewables. So today, the good news is that the world is doing pretty well in renewable development. We have about 400 gigawatts, which is like in Indian arithmetics, we would say 4 lakh megawatts of installed capacity of renewables in the world. Out of that, about 33% is in India. That is about 132 gigawatts is in India. So that's a good news. But if you look at the electricity generated from renewables, that's not very encouraging because it's still about 13% of the global electricity consumption. India also, it's almost the same percentage, about 12.9 to 13% of the electricity generated in the country is from renewables. This includes generation from hydropower, because you know the states like Kerala, where 30% of the power we generate in-house or within the state is mostly from hydropower. So that's the good news. But the second good news is that electric mobility, that is displacing oil consumption in transport, which accounts for about 24% of the oil consumption in the world. There also, from 2020, there has been a lot of movement. And this year is supposed to be a breakout year. The projections are that we will sell about 14 million vehicles, electric vehicles globally, out of the about 85 million vehicles which are supposed to be sold this year. So these are 2, I mean, even the electric mobility is quite breaking out in a big way, is going to take some time. Right now, we are displacing only about 1.5 million barrels of oil per day from the use of electric vehicles, which is not much because, but by 2050, we are supposed to displace about 24 million barrels per day. For comparison, if you know, I mean, we use about 100 million barrels of oil per day. That's the global consumption today. So electric mobility and renewables are the good news. Now, the bad news is that more than 3 decades of international negotiations and international actions, we are still in bad shape. Today, the climate has changed about 1.2 degrees centigrade. When you talk about 1.2 degree, I remember once when I was talking in Thrissur on climate change, somebody asked me, how does it matter if 1.2 degree increases, 2 degrees centigrade increases? The point is that it is based on the global average. The pre-industrial level, the global average was about 14 degrees centigrade, the average temperature. So this 1.5 or 1.2 or 2 degree increase we are talking of is from that 14 degree centigrade global average. That and what does it do to the planet? That will come to little later. How even a 1.2 degrees is very dangerous will come a little later. I looked at the atmospheric concentration of carbon dioxide as of November. It's about 420 parts per million. Pre-industrial was 280 parts per million. That's how we count the carbon dioxide. And the figures are generally put out by the Mauna Loa Observatory in Hawaii in the United States, which is right now closed for some maintenance work. But the US agencies are putting out the figures. It's about 420 parts per million. And we are at around 1.2 degrees centigrade above the global average of 14 degrees. And the projections are that, the United Nations projections are that, even the IPCC projections are that by 2030, or even before that, between 2027 and 2030, we are going to hit 1.5 degree centigrade. This is very bad news. Because even at 1.2 degree, the last few years, the world has been experiencing natural disasters at unprecedented levels. In fact, if you look at the last 10 years, it has been extremely bad. And the last 4-5 years is still further, very frightening. And there was a time when a lot of Western thinkers put out this idea that the developing countries are going to be the big sufferers when climate change happens. But what we are witnessing is that nobody is safe from climate change. Even the developed countries, including Europe and the United States, are facing the brunt of climate disasters. But there is still no realization of how to stem the tide of this climate disaster. And right now we are emitting about 53 billion tons of greenhouse gases. Carbon dioxide forms about 40 billion tons approximately out of that. Annually, 53 billion tons. To put it in perspective, you can multiply by 100, you get the crores figure for Indians, I'm saying. So 5,300 crore tons of carbon dioxide we are emitting every year. And it is not going down. The UNEP projection is that it will reach about 57 billion tons by 2030. Despite all the negotiations, all the efforts, the carbon dioxide emissions are not reducing. There are reasons for that, because renewables don't displace fossil fuel consumption. And the Paris Agreement, the 2015 Paris Agreement, which was entered into by the world community, is a demand-side agreement in the sense there is no supply-side constraints applied to any country or any producer. We're basically looking at demand-side management. That is, you produce renewable electricity, you bring in electric vehicles, etc., and manage the demand and displace other fossil fuels. But there is no real reduction in fossil fuel use in the world, and it is increasing, and that is why the emissions are not coming down. Renewable electricity does not displace fossil fuels. Maybe in some cases, to some extent, we may be displacing some coal, but the transport sector, the displacement of oil, which is the major polluter today, is not very comfortable at present. So I'll just come to, this is the picture as we talking now. We'll look at the reasons why this is happening. Before that, just one more figure. We have emitted about more than 2 trillion tons of carbon dioxide into the atmosphere. About half of it has been absorbed by the sea, the biosphere, the lithosphere, and all that. And what is left in the atmosphere is about 1 trillion. That's about 1,000 billion tons are left in the atmosphere. These figures are important because as I proceed, I'll be referring to some of these figures and how this is going to increase. Can we have the first slide, please? So before we proceed, I would like to talk a little bit about the climate system, second slide, please. The globe. How the Earth's climate system works, because we all must have studied something in the schools, but I think most of us have forgotten how it works. So the climate system is such that, as you know, towards the equator, that is the lower latitudes, it's hot because of the Earth's rotation and the sun's radiation which it receives during the rotation. And as it proceeds, we go to the higher latitudes towards the poles, it gets colder. So that's how the Earth's climate. And in the poles, as you know, about 6 months there is no sun. So that is why we have that huge ice mass sitting there. Second slide, please. And there are so many components of the Earth's climate system. I want the second slide. Third slide, sorry. Slide 3. Slide is not seen, huh? Can you see that? Can you see the slide? I'm not able to see. Okay. Why the slide is not visible, please? Can you hear me at least? Hello? Is there a problem?
So 1 second, sir.
Yeah. No, that's the fourth one. I want the third. Third slide.
So it was blank slide, sir. Sorry.
It's not blank. Because without that slide is very important, you know. The Earth's climate system, that's a slide, you know. At least on your screen, if you put, that's okay, even if you're not able to share.
1 second, sir. Let me check.
That's a very important slide, because without that, I cannot explain. You're losing time, yeah.
Some format like Shri. Slide 3. Slide 3. Go back. Go back.
Third one.
Third one is still
Blank.
okay, just tell him it's not loading the video.
He can share from there.
Can you give
We
him
have
the
the
image?
problem over here. Sir,
Even if
sir,
you,
blank slide, sir.
no, is it visible to the audience there?
No, sir. No, sir.
Why? What happened?
So it shows that the image part with the relationship was not found.
Okay, then I'll talk. I don't want to waste time, okay?
Okay.
So we have the Earth's atmosphere, which is about 10,000 kilometers above the Earth. And we have about 4 layers of the atmosphere. The first one is called troposphere. Second is stratosphere. Troposphere is about 15 kilometers, and troposphere, and then the stratosphere above that, then the mesosphere, and then the exosphere or thermosphere, as we call it. So, but the most important 2 layers the atmosphere has are the troposphere and the stratosphere. So the gases present in Earth's atmosphere, we have about 78% nitrogen, about 21% oxygen, And then the rest are trace gases like carbon dioxide, water vapor, argon, etc., etc. So mostly carbon dioxide is present in the atmosphere in trace form, like in decimal form, decimal quantity. But that's very important. The water vapor and the carbon dioxide presence in the atmosphere in that minimal quantity is important because it traps sun's heat and keeps the earth warm. But when the carbon dioxide content goes up, the trapping becomes too much and the earth gets heated up like a greenhouse. That's why we call it the greenhouse effect. The climate change, another name we will call is greenhouse effect. So what we have done after the industrial revolution is that we have been putting out carbon dioxide much in excess of what was present before the during the pre-industrial time. And as I said, right now, the accumulated carbon dioxide in the atmosphere, after about 50% absorption by the sea and the biosphere and the lithosphere, the sea absorbs about 30%. That's how the system works. I'll come to that later. So we still have about a trillion metric tons in the atmosphere, and we are at 1.2 degree centigrade temperature increase, which according to people like Dr. James Hansen, this carbon dioxide itself is enough to heat the earth much more. He calls it climate change in the pipeline. His latest paper, which has recently been published, he and 16 other authors. I consider him as the topmost scientist in the world, Dr. James Hansen, former NASA director. So that's where we stand, and what we are, the second part of the climate system, most important part, I would come to the cryosphere. The cryosphere is basically consisting, it is three elements. One is the South Pole, the other is the North Pole, and then the mountain glaciers, out of which the most important part is the Hindu Kush Himalayas, which is called the third pole actually, because about 98% of the ice is in the poles only, about 2% is in the mountain systems, and in the 2%, maximum is in the Hindu Kush Himalayas. So we call it the third pole. And then I'll first talk about the South Pole and the North Pole and how what's happening to the North Pole. The North Pole, as you know, the North Pole and South Pole have two peculiarities. Can you go to the next slide, please? No. You will have to go to the. Can you switch over to the? Sorry. Let me look at the slide. Yes, you please go to slide 7. Slide 7. Only one. I am able to see only one. Why? There are two figures in that. The Arctic is not seen. Anyway, I'll talk. There's no time. The Arctic or the North Pole is basically the center of the pole is the Arctic Ocean. It's surrounded by land. Whereas in the Antarctic, the center is land. It's surrounded by what is called the Southern Ocean. So these are two distinct features of the South and North and South poles. And the North Pole, there are two elements of the cryosphere. The cryosphere, when I say, I hope all of you understand, that is wherever the Earth is covered by ice, permanently covered by ice. So in the North Pole, there are two components. One is the winter sea ice, and second is the Greenland ice sheet, which is huge. And I'm talking about the size. I'll talk about the size a little bit later. So the sea ice is there, which is like it forms in winter. Some of it is melted away in summer up to September. Then the Greenland ice sheet is the huge ice sheet. Sometimes the height could be up to 4 to 5 kilometers high. The ice sheet could be that high. Average height is about 3 kilometers. So these are the two North Pole ice formations. And just look at the figures of this. It's mind-boggling if you look at these two. Just give me a second. Yeah, the Arctic Sea ice extent is about 16 million square kilometers. That is now thinned to about 7 to 8 million square kilometers because there is a phenomenon called polar amplification. If we are experiencing an average of 1.2 degrees centigrade temperature rise, in the poles it doubles because of some phenomena called albedo loss. Because when you have it's a complex phenomena. When temperature rise starts melting the ice loses its albedo. Albedo is basically the capacity of ice or the white surface of the ice to reflect the infrared radiation back into space. That's how our temperature is controlled, because all the sun's radiation coming into the earth, the infrared portion is reflected back by the earth, and maximum reflectivity happens in the poles, and that's called albedo. So because of this complex phenomenon of warming, melting, when the ice thins down, the albedo goes down. That increases the warming. So in the poles, the phenomenon is called polar amplification, mostly in the northern polar region. So it's almost double or sometimes 3 times the global average temperature increase. So it's like a vicious cycle. The warming leads to more warming, it leads to more melting. So the poles, the Antarctica and the Arctic and the Antarctic, both are in danger. I would like to come to that a little later because I have to explain the other components of the Earth's climate system. Can you? Okay, the second one is the ocean. The ocean plays a very major part in controlling the Earth's climate, because you all know we get rains because of the evaporation from the oceans. And the oceans have another big role because about 30% of the carbon we generate is absorbed by the ocean. And in normal times, ocean has the capacity to keep the homeostasis of the Earth going, but that is in millennial scale. You talk about thousands of years history of the Earth. The cycle, the carbon cycle, what is called, I'll come to the carbon cycle in a little time. The carbon cycle is moderated by the ocean. And what is carbon cycle? Can you do that carbon cycle slide? That is number 4. Number 4, please. Yeah. The Earth, approximately, the Earth has about 65,000 billion tons of carbon stored in various forms. Out of that, about 10,000 billion tons are stored in fossil fuels. You know, fossil fuels are basically decayed organic matter stored beneath the earth or over millions of years. So whatever we are excavating now and burning, fossil fuels, whether it is coal or oil or gas, natural gas, these were formed over millions of years due to the photosynthetic activity in the earth and the plant material going down the earth or millennia and then decaying. In fact, it is in semi-decayed form on which microbes work, and then they are converted to different forms of fossil fuels. I can't go into the details of each fossil fuel. I can only say that these 3 sources are formed by decaying of organic matter over billions of years. And what we are doing is putting out this 10,000 billion tons of carbon, which is below the earth, by burning the fossil fuels in a period of about 200 years. As I told you, we have already put out more than 2,000 billion tons into the atmosphere. So the other carbon is stored within the ocean. As I said, then carbon is stored in our, what you call the rocks in the earth, because roads, and then the rains wash away some of the carbon, because when rain forms, a part of the carbon in the atmosphere is washed down to the earth as carbonic acid. That sort of, again, the slides have gone. Okay, I'll continue to talk if it is on the screen. So the carbon forms a cycle, like carbon is stored beneath the ocean in sedimentary form. During the rains, the evaporation happens, the rains wash out more carbon from the earth and the atmosphere. This cycle takes millions of years, so the homeostasis of the earth is maintained. What we are doing now is taking out the carbon in large quantities and pouring it out in the atmosphere in quantities which nature cannot handle. So that is how the carbon cycle works. And the carbon cycle has been disrupted by anthropogenic force. That's why you all know that our age now is being renamed as Anthropocene. We have been living in the Holocene for last about 12,000 years, maybe 11,700 to be precise. But scientists are now in the process of renaming our age as the Anthropocene because of our intrusions into the Earth's environmental systems, including the climate system. So Anthropocene is very prevalent in the cultural discourse, but in I don't know how many common people know that we have already entered a new era called Anthropocene. So that's the second part of the major part of the carbon cycle is a major part of the climate system. And now let's look at what is happening to different components of the Earth's climate system. There has been a study put out in 2008 called Climate Tipping Elements Study. It's from the Potsdam Institute of Climate Change Research. Dr. Timothy Lenton and his co-authors put out the study looking at about 13 tipping elements of the climate system. And then recently in 22 September, they put out another study increasing the tipping elements to 16. I'll briefly go over some of them. Can you go to slide 5, please? I'm not seeing any slide actually.
So 1 second.
Just show it to you.
Sorry. Slide 5. Fine. Slide 5 is titled the 16 climate tipping points.
So it's the same.
Same.
Yeah. Just tell it. It's
You see it?
The file is having the same issues as before. I mean, the fifth one.
Can you see it there?
No.
No, sir.
Oh God. You should have checked earlier and told me, no, I would have done something, but it's a pity. Okay, I'll go over one by one. I was earlier talking about the poles, which are major tipping elements in the climate system. And I said about the North Pole, there are two components, the winter ice, winter sea ice, and the Greenland ice sheet. Let's give you some figures of how bad this could be when they, as I said, the winter sea ice is about 16 million square kilometers originally. It is now thinning down to about 7 to 8 million square kilometers. And in fact, in 23 summer, it has thinned down to about 5.6 million square kilometers. So it's disappearing very fast. It's also disappearing in thickness. It used to be about 7 meters thick, which has now come down to about 4 meters. So that's because of the warming which is happening, and it's not good for the albedo. And there is a feedback cycle that as the ice goes on reducing, temperature also decreases the albedo. So the warming increases. The next one is, of course, the sea ice melting does not increase sea levels because the water for the ice formation has been captured from the sea only. So it doesn't increase sea levels, but it will drastically affect our global climate. This year there is an El Nino happening, as you know, a dry El Nino is happening. It is attributed to the changes in the polar regions, actually, one of the reasons. And also the AMOC, the Atlantic Meridional Overturning Circulation weakening. I'll come to that later. So, but if the Greenland ice sheet melts, which could be really deadly, I mean, Greenland ice sheet, the size is about 1.73 million square kilometers. Just imagine 1.73 million square kilometers with an average height of 3 kilometers, how huge that ice sheet is. And if all of it melts, it could raise sea levels by 24 feet. Of course, all of it is not going to melt immediately. That's the good news, but it is melting. And Greenland temperatures have gone up. There's something called surface ponding happening over the Greenland. Surface ponding is when Greenland ice melts and ponds or lakes are formed on top of the ice sheet. This is very bad because it causes something called hydrofracturing. Hydrofracturing is when this water formed in the lakes on top of the ice sheet goes down through, cracks formed in the ice sheet. It's called vertical cracks called moulins. Scientists call it moulins. And then it goes down to the bottom of the ice sheet. It destabilizes the ice sheet. So this process is going on and there is also last year, actually it rained in Greenland. First time in history, known history, it rained in Greenland, which worsens the melting of the ice sheet. And Greenland ice sheet, it is slowly melting. And it is, according to NASA, it has been losing 270 billion tons of ice in the last 20 years. These are NASA figures. IPCC has put up a slightly different figure, but I tend to trust NASA because they have a satellite system called GRACE, completely focused on the cryosphere, and then monitor the cryosphere through these satellite systems. So it's losing about 270 billion tons in the last 20 years. It has been losing. And as the melting proceeds, the sea level will continue to rise. Now the sea level rise is, of course, if you look at it, 0.8 million millimeters, 0.8 millimeters per year, which may look very small, but if you talk in the next 20 years, it could be very high. Then it is the Antarctic ice sheets, which is supposed to be safe. Can you put that one slide which you had, the Antarctic at least, that is number 7? I need that, number 7, because difficult to explain without that. We are losing time, I don't know. I may need to extend up to 10:30, I'm sorry, yeah. Okay, no, number 7, next one. Yes, so here you look at your left side, that is called the West Antarctic ice sheet. On the right side, the big one is the East Antarctic ice sheet. The West Antarctic ice sheet is already in danger. And Antarctic, you look at the figures actually, Antarctic holds about 90 more. It's about 19.47 million square kilometers. That was the extent of Antarctic ice sheet only. And because the terrestrial ice at the center is much more. As I said, the sea ice melting will not raise sea levels, but if the terrestrial ice in this West Antarctic ice sheet and the East Antarctic ice sheet melts, it holds 91% of the world's ice. It can raise sea levels by 239 feet. That is about 73 meters. It's that bad. We thought Antarctic is safe, but the latest research, I have looked at research right up to November 23, because basically I'm doing this also for a book I'm writing on the our future in the Anthropocene. So latest figures I have looked at, the news about the West Antarctic ice sheet is very bad. It is getting destabilized also because the base of the ice sheet, West Antarctic ice sheet, is 6,500 feet below sea level. So as the ocean is warming, oceans are warming. Ocean warming is slightly higher than the terrestrial warming. In fact, some of the phenomena you're seeing in Kerala and both in the Bay of Bengal and in the Arabian Sea around India are because of ocean warming. It's above actually 1.2 degree. So the natural disasters you're seeing is partly because of the ocean warming. So ocean warming is slowly destabilizing the bottom of the West Antarctic ice sheet because it's grounded at about 6,500 feet below sea level. That's how the West Antarctic ice sheet is. And West Antarctic ice sheet itself has the capacity to raise sea levels substantially if it melts. And according to NASA, it's a November 23 figure I'm saying, the Antarctic as a whole is losing about 150 billion tons of ice per year right now. And it's very bad news for us. As I said, even the West Antarctic ice sheet itself, especially there is a glacier called Thwaites, which is called, what's it called? I'm just forgetting the name. Doomsday Glacier, sorry. Doomsday Glacier. That's in extremely bad shape. That is supposed to break out in the next maybe a couple of decades. And this is extremely bad news. Even the West Antarctic ice sheet, if it melts, it can raise sea levels substantially. I have to go fast because I'm looking at the watch. Then we come to another major element in the climate system called AMOC. AMOC is called Atlantic Meridional Overturning Circulation. Can you put that slide, please?
Ask which slide.
No, 1 minute. I'll tell you the number. Yes, slide 10.
Slide 10.
Yes. Picture is not there.
Say no.
You're not getting the picture. Oh, God.
No, I think you've stopped sharing. Share it.
Even if you get it on your screen, it's okay.
Yes, without sharing, you try. No.
It's very difficult to explain without putting the slide.
Slide 10.
Is it on your screen at least?
So 1 second, sir.
Yeah. Ten.
So the same issue itself, sir.
Can somebody just type a mock diagram on somebody's laptop and show it to the audience, please? It will be easy for me to just type AMOC, AMOC diagram. Just put a color diagram and show it to the audience, please. Then it will be easy for me to explain. You're able to get it? Okay.
If you're not able to find these slides, I think, sir, you should continue. I have a feeling it's going to be hard. Can you find these slides?
No, it's not.
Just put on your internet, just search for AMOC, and that I think we can do with that. Okay, can I go ahead?
Yeah.
This is it, right?
Okay, AMOC is called the Great Ocean Conveyor or the Atlantic Meridional Overturning Circulation. And it goes all over the world to all the oceans. It connects all the oceans. Why it is called a overturning circulation is it's a kind of circular system where there is a upper warm layer, upper warm current and a lower cold current. How it forms is it starts basically in the poles when the ice melts naturally also. So the fresh water, then when the ice melts, the density of the sea increases because the salinity increases. There are two factors which increase the density of the sea. One is the salinity increase, and the second is the cold temperatures. So in the poles, when the seas are very extremely cold and the density increases because of the ice melting, the water sinks to the bottom. That cold water sinks to the bottom, then it goes down, and somewhere else in the mid latitudes, it rises up. It's called downwelling and upwelling. And after upwelling, it captures heat from the atmospheric winds, which are basically called gyres, Gyres, which conduct the heat from the equator towards the poles. So there is a wind system which moves from equator to the poles, and there are trade winds. Then there are what is called gyres, which are formed due to the wind. Gyres are basically ocean currents. So the atmospheric heat is absorbed by the overturning circulation, and the upper layers are kept warm from that. There's also a speculation that the heat is also absorbed from the Earth's core. Anyway, this AMOC regulates the world temperature in a very big way, especially European and United States temperature of these two continents are directly affected if the AMOC weakens. And the bad news about the AMOC is that the AMOC is weakening. This is not a joke. No, the AMOC moves faster means the volume of water moved is much bigger than the Amazon's water volume, which is something like 20 million cusecs a second or something. So it's a huge conveyor, which if it weakens, the movement is slow. Movement is not very fast, but the amount of volume and the nutrients and the oxygen circulated in the ocean is very critical. And any weakening of the system is going to be very deadly for the global climate. And some of the things happening today is already